Why, hello, lovely humans. Welcome back to Center of Mass. Oh, yeah. All right. So, in part A, we figured out how to calculate the center of mass of a system of multiple objects. But now we calculate the center of mass for a single and slash continuous object. Continuous just basically means like it's one whole solid object. Cool. So, in any physics and engineering problem, there are always certain assumptions that we are going to be making. Most of those assumptions are to make our lives easier. So, like in the seesaw problem, instead of drawing a complicated shape of a human body, it's a lot easier to just say, it's like a circle. And that's, fairly accurate, right? Because even though we have arms and legs and a head, the center of mass of our whole body is basically in, well, the center of our torso. That does actually change, and y'all folks who are dancers or ballerinas or ice skaters will recognize that the location of your arms and legs can change your center of mass to help and or hinder spinning motion and doing fancy twirls and things like that. Anyway, all that being said, you can actually calculate that. But let's start simple with a straight bar. And so in this case, we are going to assume that the mass of this bar is distributed evenly. Basically, that like when you pick up the bar, the weight of it, you could flip it over, you could hold it in either direction, and the weight of it would be kind of uniform throughout. Another way to look at that is to say the linear density of the object is just the total mass of the object, which I'm going to denote with a capital M. So the ln density is just the total mass of the object divided by the length of the object. And that just says that the mass is distributed evenly across the whole object. Cool. Okay. So that's a very important distinction. So now we're going to say, all right, let's set up our coordinate system. Oh, it's kind of hard to... We'll set up our coordinate system at the end of the bar. And so at that point, we'll say, okay, x equals 0 here. We want to find the center of mass of this object. And so that basically means that our weighted average is going to turn into an integral, because what we're going to do is, you can think about this like we have our weighted average, but instead of just like one object, two objects, three objects, we're adding up a ton of teeny tiny little objects within the bar that we are going to call, rather than M1, M2, M3, etc., we're going to call this dm. And this is just kind of standard calculus notation. dm basically just means a very tiny slice of this object. The idea is that you get this little chunk as small as possible, so that at a certain point you could say this is like one part of the mass of the object. And so then you basically have to say, okay, well, for this teeny tiny little slice of the object, what is this? How can we represent this? What is the actual mass of this tiny slice? Well, the width of this tiny slice is a tiny length of the object. And so you could say, well, the mass of this teeny tiny slice is the linear density, which is capital M divided by L, times the length of that tiny slice. And alternatively, you could also say that the length of a tiny slice is equal to the total mass of the object divided by the length of the object. So basically, this is a way to calculate a tiny chunk of mass of the object. And what that does for us is it allows us to simplify some things. So first, let's take this equation and write it in integral form. So x of center of mass is going to be equal to the integral over the mass of the object, where we have x, where x is this distance. So you can think about x like, okay, so when x equals 1, we're adding up a certain amount of dm. When x equals 2, we're adding up another slice, another slice, another slice, and so on and so forth. So you have to multiply each of the lengths of those slices by the mass of those slices, and then you divide by the total mass of the object. So this is actually the same equation. It's a little hard to see unless you're super familiar with calculus, but on the bottom we have total mass on the bottom here too, and on the top we have a weighted average with respect to the mass of the object. But in this case, rather than these discrete different objects, we just have these tiny little slices. And so the weighted part is the distance of that object from our origin point, where x equals 0. Okay, so now that we have translated our discrete equation into a continuous calculation, where we are adding up over the entire length of the object, we can get moving. Okay, so fortunately we did the hard work first, and now we can substitute in for dm. We can't take the integral right now because we don't know without substituting how x depends on dm, so we can't really take the integral. We do actually have two options here, I suppose, but the best way to do it is to replace dm. So what you do is you just rewrite the integral in terms of dx. So we are substituting this equation for dm in. So we know that dm equals the total mass divided by the total length times dx. But we also have to change our limits, right? Because now all of a sudden we're not integrating over the mass of the object, we're integrating over the whole length of the object. So x stays the same, and we substitute in for dm, m over l times dx, and then we still divide by m. And so now we can actually do the integral. So we pull out m over l, we get to cancel this m with that m. We're integrating over 0 from l from x times dx. And so then what we get is 1 over l times 1/2 x squared from 0 to l. All right, so we're getting close, and we find that we have 1 over l times final minus initial, so we're going to get 1/2 l squared minus 0, which just equals l over 2. Boom! QED. So basically what this tells us is that the center of mass for an object of uniform mass distribution is just the center of the bar, which is what we expected, right? Hopefully. And if not, this is the mathematics behind that intuition. And this is really important to know because not all objects are going to be this simple. For example, a trapezoid can be a little bit tricky. But also I think it's really important to do practice problems that match up with our intuition to get a feel for how the math works, so that when we have to do something that's, a little bit different, or maybe we have a bar where it's weighted really heavily on one side, we're going to get a different answer. So we need to understand how to use the math so that when we do a problem that we have no idea about, we can make sure that we're getting the right answer. Very important. Okay, so I do want to end by giving you a practice problem. And so this practice problem is going to be calculate the center of mass for a rectangle of length, we'll say length equals 2 meters and height equals 5 meters. So that is not to scale, but that's why you get to calculate it. Okay, so what is the center of mass for this object? And I want you to go through this process. A little bit of a hint, it might be a little bit more challenging because you're doing this in 2 dimensions. Let me know if you have any questions about that. Cool. Okay, so there you go. This is how you calculate center of mass for an object with uniform mass distribution. Let me know if you have any questions about this, about center of mass in general, or about this problem. Yay! All right, thanks for watching, and we'll see you next time. Bye!